Everybody needs to.
Okay, so let's go ahead and begin. Okay, so today's lecture should be relatively short. It's going to depend on how many questions, but I don't have a whole lot to go over. Just what the auto wrapper is and what's its purpose. Also, I think this is a good time to talk a little bit more about hardware 6 and also the final project, the hardware part of the final project. Okay, so you can see, what's required for both of them. Because after we talk about the auto wrapper, you'll be able to do both. Well, even before today's class, you could do hardware 6. But then after you know about the auto wrapper, you'll be able to do the final project also. And as I mentioned prior to today, hardware 6, it's due a week from tomorrow. Okay, so March 3rd. And then the final project hardware is due the last class day of the quarter, which is March 17th. So that's due like 3 weeks from now. So I just want to go over some of the things I've already talked about regarding hardware 6. First of all, and I covered this not last class, class before. So it was a week ago today. It was the first meeting on the control unit. And I outlined during that class, and if you missed it, the notes are on. But during that class, I outlined, what the Verilog or system Verilog code would have to look like to model your control unit FSM. Now, we talked about the write back state last class. And remember, the write back state is only necessary for load instructions, like load word, load byte, load half. You don't need a write back state for load upper immediate, right? LUI, because again, the data path to that instruction doesn't go through the memory module like the other load instructions do. So for hardware 6, your FSM doesn't need a write back state because hardware 6, you just want your Otter, right? The CPU, your Otter CPU, just to run that program that has 6 instructions. Right, the same program that I had you do the activity timing diagram for. So since none of those 6 sample instructions are load instructions, hardware 6, the FSM does not need a write back state. Okay. So I outlined how to do the FSM, like I said, a week ago today. In fact, I gave you the code for the state register. I gave it to you, so you have that. But then we talked about the state decoder. And remember, the only thing that happens in the initial state is that's when the program kind of gets reset to 0, right? So we started instructions. And then the only thing that happens in the fetch state is your mem RD enable 1 gets activated to 1. Want to get the instruction at the output of the memory module. So really, where the work lies is in the execute state. Right? Because that's when you have to look at the instructions and see what read enables and write enables have to be activated for that particular instruction. Okay, so that's where your case statement's going to be, based on opcode. Okay, again, I outlined it, so we're just going over things we already talked about, but I'm just reminding you before we go to do stuff. Also, your control unit decoder. Right? You're going to have to do some work there also based on the instructions in the opcode because remember the control unit decoder, that's outputting the selects for the muxes, right? And depending on what instruction is being executed, well, different muxes or muxes selects have to be different values, okay? So again, I know I keep repeating myself, but in order to model these control units, you need the data path and the control signals for all real instructions. Okay, anytime somebody comes up to me and says, any sort of question about what should I do here with the control control unit, I always go, well, you have your diagram for that instruction. You know, because that's always where you start, okay? Okay, so hardware 6, you gotta model the FSM, you gotta model the control unit decoder. Also, this is when you connect all your lower level modules together. Once you have those control units done, now you have all the pieces to the otter, right? You know, we've been doing a piece basically one per week about. Well, now you have to come up with a top module that connects them all together. Right? You've done that plenty of times. You've done it, well, you did it for the program counter, right? One of the first assignments we did here. And you did structural models in CP133. So you should be very familiar with how you have to do the code in order to connect up those lower level modules. In addition, you need 3 more muxes, right? Because you've done the mux for the program counter, but there's 2 muxes at the input of the ALU, and there's also a mux where the reg file is, where the right data input. Now, like I mentioned last time, you could put those muxes in the top module. You can put case statements right in the top module, and 1 case statement for each of the muxes. Or you could just use, you know, design source file for the mux. Okay. Now, the groups and the grading criteria for hardware 6, it's the same as all the previous hardware assignments. Okay, so it's the same teams and you know, same grading criteria, nothing different there. You'll see that there's some options for groups, and also there's different grading criteria for the final project hardware. Now, but once you have this, right? Once you've done the modules and co-modules and you've done the top module, watch this video. Okay, I have it up on the screen here. It's under meeting 11. This is meeting 12, so it's under the last meeting we had. But this is a video by Dr. Hummel. It's hardware 6, Dr. H. And at the 26.5-minute mark on, he showed how to do the sim and what to look for in the sim for hardware 6. So, you know, when you go to simulate your hardware 6 and you're looking at the timing diagram that it gives you, well, it should match what Dr. Hummel has. Also, it should match what you have on that timing diagram that you did for the activity last class, provided you did that right. Now, you can check your timing diagram that you did on paper to Dr. Hummel's to see if it's correct. Okay. So, do you have any questions up to this point? Because, like I said, this isn't really anything new. I'm just kind of summarizing some of the things we discussed earlier. But I'll start into new stuff if you don't have any questions up to this point. You're all good? Has anyone started hardware 6 yet? Few people? Okay. Yeah, don't put it off too long. I would definitely, if you haven't started it, I would definitely start today once I'm done. See, the good news is that once you have hardware 6 working, when you go to the final project, you won't have to modify the top module, right? Because the top module is not going to change between hardware 6 and the final project. See, where the work is going to be in the final project is the state decoder, execute state of the FSM, and also the control unit decoder. Because the big difference between hardware 6 and the final project is in the final project, you have to have your CPU, your Otter CPU, execute every instruction, right? All real instructions, not just 6. So that's where you're going to have to modify. You're going to have to modify the execute state of your state decoder, the FSM, because you're going to need the read-write enables for all instructions. And then here for the control unit decoder, you're going to need the mux selects for all the instructions. Okay, we'll talk more about that coming up when we get to the final project. Okay, but the next thing that I want to talk about is the Otter wrapper. Okay, the Otter wrapper is circuitry that goes around your CPU, and it interfaces the Otter CPU to the outside world. So it's going to interface it to inputs input devices like switches and output devices like LEDs and 7-segment displays. We provide, or Dr. Hummel provides the auto wrapper. Okay, he designed this. Now, you'll have to most likely do a little modification to it that I'll get to in a little bit. But this is what the auto wrapper looks like. Here's your CPU, and here's the high-level black box diagram of the Otter CPU. If you look on the Otter architecture diagram, they're all very close now. In the upper left corner there is this same diagram, okay, the high-level black box diagram. And you can see that the Otter CPU, it just has a few inputs and 3 outputs. Over here on the input side, we got our reset input. We have our IO bus in, our clock. Now you put interrupt, the interrupt input in red because we're not covering interrupts, right? We're not dealing with interrupts. So you can either omit it, don't even declare that input, or if you declare it, just set it to 0. And then we only have 3 outputs. IO bus write, IO bus out, that's your data out, and IO bus address. So in your top module, right, you're just going to have to declare, 3 input and 3 outputs. Okay, so there's that many main inputs and main outputs to our Otter CPU. So here's the Otter CPU connected to the wrapper circuitry. And when you look at this, most of this you've seen, most of these symbols you've seen before, right? You've seen this symbol. What's that? The MUX. Okay, you've seen something like this, a divide by 2 for the clock. Right, you see that in CP133. We talked a little bit about this, but and also this is covered in CP133. What's the clock frequency of the basis 3 board clock? That's 100 megahertz. You see we're dividing that down by 2, so 50 megahertz. Here's the output, and that's what operating our Otter CPU as well as this other circuitry that you see over here that's sequential. Now, I think I mentioned this before, but I'll say it again. The reason we're dividing the basis 3 board clock frequency down to 50 megahertz is just to get some wiggle room in your design. Okay, by slowing down the clock, if your CPU isn't super efficient, it still should be okay. There could be a possibility where if you run it at 100 megahertz, due to propagation delays, say in your execute state, that maybe it wouldn't work quite right, maybe. But under that same situation, it could work with the slower. Okay, so again, this is just to give some margin of error, again, to provide some wiggle room. Okay, over here, this is the decoder that's operating your 7-segment display. So this is a decoder just like the one you saw in CP133. I mean, it's not exactly the same, but it's doing the same purpose. What are these here? You got a D input, Q output, enable, it's sequential, flip. Yeah, those are just flip-flops, registers. Okay, now this symbol here you might not have seen. In fact, in my CP133, I don't think I mentioned this, but you might have seen it with a different instructor. Did anyone see this symbol in their CP133? I mean, in my earlier section, there were some students that had seen it. This is called a DMUX. A MUX, a multiplexer, has multiple inputs and a single output, and the select chooses which input gets connected to the output. Well, a DMUX is just the opposite. A DMUX has a single input, has multiple outputs, and the select chooses what output the input gets connected to. Right? So a DMUX is just a MUX working in reverse. Okay? Now, a good thing to notice here is, see this IO bus address? It connects to the selects of the MUX and the DMUX. So at this IO bus address, it's gonna be the addresses of your input devices and your output devices. So for example, when you have some, instruction dealing with switches, do you remember what address we're using for the switches from your assignments?
I think you're,
All zeros, right? Yeah, so to choose the switches on this address bus would be the hex 11 all zero. Okay, that's what we would have on this select line. And that would connect the switch input to this output that goes into the CPU IO bus in. So the switch data goes into your CPU. Now, you might notice that the other input here to this MUX is just labeled inputs, okay, very general. And that's because the way the wrapper, the default code of the wrapper just has switches as an input to this MUX. But it has the flexibility, the code has the flexibility where you could add inputs here. You could add more than one more input, you could add a number of inputs. So, you could add like a keyboard or like a scanner or some other input. Now, for this class, because we didn't have time to do interrupts, we're going to be limited to just switches. Okay, because in order to use, say like a keyboard as an input, you would have to also include an interrupt. And again, we didn't have time to cover that. Okay, so we're just going to have switches, but it's good to know that you could add to this because if in a future class, if you use the Otter or just on your own, if you want to use the Otter, you have the ability to add more inputs if you want to. Okay, over here on the output side with the DMUX, it's the same sort of thing. The address is what's connected to the select line. So the address is going to determine what this IO bus write output connects to, whether it connects to the enable of this register or the enable of this register. This register is holding data for the 7-segment display. This register here is holding data for the LEDs. So do you remember the address for the LEDs from your assignments? Right, it's the switch address plus 20, right? It's the 11.0.0.0.20. So that's the address we would have here if the output data, and the output data is coming from this IO bus out. Okay, but that output data won't pass through the register unless the enable is activated. Okay, and it's an active high enable, and that's coming from this IO bus right. Okay, and then if the 7-segment displays are being used, well, you would have address 11.0.0.0.40 hex, and that would select this enable here to register for the 7-segment data that goes through the decoder. Okay, so the short of it is that this wrapper, again, that we provide, Dr. Hummel again designed it. It's what's interfacing your CPU to the switches and also to output devices. Okay. Now, where you might have to modify the code in the auto wrapper, and this is a good time to bring up a couple of other videos that I have. Okay, that video there that we just talked about a moment ago, that's under meeting 11. Under meeting 12, there's a couple more videos, one that I made and another one by Dr. Hummel. This one that I made here, I show you in that video what code, like where in the auto wrapper code you may have to make some modifications, because Dr. Hummel probably didn't name his inputs and outputs of the high level black box diagram. So these named outputs. He probably didn't name them the same that you did. Okay. So you're gonna have to go into the auto wrapper and make modifications to these names where they connect to the rest of the circuitry here. Okay, so it's not much to keep that in mind. And like I said, I show you in the video where it is, like where in the code. Okay? There's some other things I go over in this video that I'll talk about coming up. And then also this video by Dr. Hummel, this is probably one of the most important, well, I would say it is the most important video this quarter. Because this video, he shows you how to debug your otter. Because you will have to debug it. You know, we've talked about this before. There's no way around it. When you have that all put together and you go to test it to see if it can run every instruction, right? And there's like 30 some odd of them. You're going to have errors, right? Everybody gets errors. When I did this, I got errors. You know, Dr. Hummel, when he did it, he got errors. Everybody gets errors. Okay, so this video, Dr. Hummel does like 5 or 6 examples of, you know, he purposely put some errors in there and he shows you how to find them, you know, the process of finding them. And that's really what's important. The important thing to get from that video is the process you have to go through in order to do the debugging. It's not so much the actual problems he's finding, because chances are you're going to have a different problem than, you know, what he put in the video. Okay, but again, it's the process that's important. And I'll talk a little bit about that process coming up. But right now, I just wanted you to know where the videos are. Okay, these 3 videos, right? 200 meeting 12 and the one under meeting 11. Very important to watch for both hardware 6 and the final project. In Dr. Hummel's video, he's going to be saying hardware 7. Okay, well, whenever he says hardware 7, that's final project for us. Okay, because if you look at the lab manual, you know, there's a hardware 8 that's on interrupts, or I think it's hardware 8 that's on interrupts. And again, we're not going to get there. So, you know, our final project is before the interrupts. It's actually, our final project is actually hardware 7, along with a little bit of a modification that, you know, I'll talk about coming up. Okay. All right. So everybody good up to this point? Because I'm going to shut off this projector and show you what's behind the screen. So now let's talk about the final project. And, you know, one of the things I want to make sure about is I want you to know, you know, what's required for hardware 6, what's required for the final project, and not to get them mixed up. You know, not to do more than what you have to for hardware 6 and not to do enough for the final project, okay? Okay, so for the final project, now, again, the due dates, hardware 6 is due a week from tomorrow. Final project hardware is due 3 weeks from tomorrow. Okay, that's the last class day before finals week. Hardware 6, again, does not need a write back state, right? Because none of the 6 instructions in the sample program is load word or load byte or load half word. But the final project has to run every instruction, right? It has to execute every instruction. So you will need the write back state in the FSM for the final project. So that's, you know, something you're going to have to modify, right? You're going to have to put that in there because it's not in there for hardware 6. Also, you're going to have more code in the execute state of the state decoder for your FSM, right? Because now every instruction, you have to tell it to read and write in 8 instead of just 6. For your control unit decoder, you're going to have to add stuff, right? Because now you need all the mut selects for every instruction, not just the 6. Okay, but like I said earlier, you're not going to have to touch the top module. If your top module is good for hardware 6, it's good for the final project. Okay, so where your work is going to be in the final project is the FSM control unit and the decoder control unit. So once you've done these modifications, watch Dr. Hummel's meeting 11 video before the 2630 mark. Okay, for hardware 6, watch this video for after, because we talked about how to sim hardware 6. But before the 2630 mark, he's talking about things that can help you with the final project. Because he's talking about how to look for patterns. Okay, and I actually have a little ungraded exercise. It's a handout on every table. It's ungraded, you know, I'm not going to grade it. You don't even have to do it if you don't want to, although I strongly recommend that you do it. But that handout also has like examples of what's meant by looking for patterns. Okay, because there's no one way to design this otter, right? I expect to see, however many groups we end up with for the final project. Like if we end up with 10 groups, I expect to see 10 different designs. Right, everybody's control unit, the FSM, along with the control unit decoder, it's going to be different. I have 6 working otters. You're not impressed. My other class was impressed, but you don't seem impressed. Okay? But I do have 6 working otters. Now, I didn't do all 6. I did one otter that doesn't have an interrupt. I have Dr. Hummel's otter without an interrupt. And I have an ISA that, a student that ISA'd for me in the fall. I have her otter without interrupts. And then I have 3 otters that do have interrupts. Okay. But of the 3 that don't have interrupts, the one I did, Dr. Hummel, and the one my ISA did, mine's the most brute force way. Now, it's not as though, I have, a case statement that's got like 37 options where, I'm basically just brute forcing it, and doing 37 instructions separately. But my otter, I basically have nested case statements or like an if within a case. The ISA, her otter, more efficient than mine. In fact, when I looked at hers, I was like, boy, this was clever. I didn't see this commonality or this pattern. And then Dr. Hummel, I look at Dr. Hummel's, his design for his otter without interrupt, and I want to cry. It's just so beautiful. Especially compared to mine. It's just like no comparison. But the thing is, you're not graded on efficiency. So whether you do it the brute force way, which I wouldn't recommend because it's a lot of code, but whether you do it that way or you do it some clever way, they're both equally good grade-wise. Okay? But yeah, there's more than one way to do this. Okay? There's not just like one way. Okay, so we talked about that you're going to have to modify your control units. Watch this video. Then watch my meeting 12 video. Okay, because what I show you in that video is how to determine whether your otter will pass this test that shows that it will execute all instructions. See, we have this mem file, okay, all test mem file, it's on Canvas. That all test mem file has 4,000 lines of instructions. You look at it, it's a huge assembly language program with 4,000 instructions. And that mem file tests every instruction. It will test all your real instructions. So if your CPU, your Otter CPU passes this, that means it's working, okay? And in this video, I show you what you need to do in the sim, the Vivado sim, to make sure it's running that mem file correctly, okay? Now, this will also be a good time to watch Dr. Hummel's troubleshooting video, okay? Because like I said before, you will have problems. When I did mine, I probably had about a dozen problems, and I was super careful. I simmed all my lower level modules. I was super careful, connecting everything together. But I had a bunch of silly mistakes. I had some things connected wrong. I remember that, at the immediate generator input, you're taking 25 bits of the instruction. I think I took 24, like I was off by 1 bit, silly stuff, mostly. I did have one weird problem that I still don't really know what was wrong, but it was a problem with the reg file. Okay, the reg file wasn't doing what it was supposed to do. And, I troubleshot it using a process just like Dr. Hummel. And I knew the problem was the reg file. Like I isolated it where I knew it was the reg file. But everything looked good. And I didn't re-sim it, and probably I shouldn't have, but when I originally simmed it anyway, seemed okay. But to make a long story short, and I just did this basically out of frustration because I knew the problem was there, but I couldn't see the specific reason why. But what it ended up being was the assign statements for the async reads. And my understanding is it doesn't matter where you put those assign statements, in your, in your file, in your Verilog, because they continually happen. But for whatever reason, when it wasn't working, the assign statements were below the always FF block where the synchronous write was. And all I did was I put those assign statements for the async reads, I put it before the always FF block, and that fixed it. But it seems to me that it shouldn't have worked either way. So I'm not sure why I fixed it, but it fixed it, So sometimes weird stuff like that happens. Another weird thing that happens, and I might have mentioned this earlier in the quarter, that I have a good Otter CPU, like I just mentioned, and it passed the all test mem in the Vivado sim. Also, once you have it working in the sim of Vivado, you then want to test on the board. And you see, this is when you need the auto wrapper, is that once it passes the all test in the sim, you then want to see whether it passes the all test on the board, the actual basis board. And that's when you're going to need the auto wrapper along with the constraints file. Right? Remember the constraints files from CP133. You haven't needed a constraints file until now in this class, but that's what maps your inputs and outputs to the actual devices on your basis board. Well, we give you that constraints file, okay, for the wrapper. So we're not only giving you the wrapper circuitry, but also the constraints file. Well, now you have to test to see if it works on the hardware. Basically, it's working with the wrapper and working on your basis board. Well, with my design, that was fine. But when I went to program it with one of the exercises that we did during the quarter using some switches, it wouldn't work with that program, even though I knew the program was fine because I tested the program out on ROS. Okay, so that wasn't working, and then I just said, well, I'll try another board, right? But it took me about a week to find another board because they're not where they usually are here, and I have to track them down. But anyway, I come back a week later, and I said to myself, well, before I try this new board, let me just try it one more time, just to make sure it's still doing what it was a week ago, because a week had passed, and it worked. So the only thing I can think of, it was either like some switch that was dirty maybe, or maybe it was just I had to restart the program, because that's one thing I didn't try, is just restarting the program. But anyway, weird stuff comes up like that sometimes. But a lot of troubleshooting, besides the right process that Dr. Hummel shows you, but a lot of troubleshooting is just being persistent, just not giving up. A lot of it is just that. But in my video, in this meeting 12 video, I show you what it should look like on your basis board when it's working correctly. And what you'll see in the video is that on your basis board, when it's running that all test mem file, where it's checking, the 30 some odd real instructions, is that you'll see the LEDs lighting up right to left. And then you'll see the 7-segment display increment by 1 in hex. So we'll start at 0, and you'll see the LEDs flash, and it'll go 1, LEDs flash 2, LEDs flash 3, and so on. Each time an LED flashes, it's doing a test. And some instructions take 16 or more tests before you can say it's good. Other instructions may only take 4 or 5 tests before you can say it's good. So, sometimes you'll see all the LEDs light up across and it increments. Other times you'll see maybe 6 LEDs light and then it increments. Okay. And you should see the 7-segment display increment from 0 to 24 hex. What's 24 hex in base 10? 36. Right, 2 16s and 4 1s. So it's basically doing 36 tests. Okay, which is about the number of real instructions we have. Okay. So if that all works, right, the sim works on all tests, the basis board works on all tests. Well, now you can go ahead and program your Otter to do something, right? Because, you know, that's why we did all this, right? We wanted that hardware to work because now we can program it to do something. So for the final project, I want you to program the Otter with one of the software assignments you did previous in the class or one of the examples I did in class. Remember how most software assignments I did like one part in class and then you did the other part? Well, you can either take one of those programs you did or one of the programs I did in class and just show that you can program it and the Otter does what it's supposed to do. Now, you'll have to add a delay. Okay, whether the delay is on the input side if you're using the switches, or whether the delay is on the output side, say if you're outputting the differences, you know, like you're calculating a difference and then outputting it to the 7-segment display, and then you know doing another difference and outputting it again, like you did for the software 5, right? When you're doing the differences between the two sequence numbers, you know, you would have to put a delay there. Otherwise, you know, when you look at it, it's just going to be, you know, gibberish, right? And on the input side, if you've got switches, you'll need a delay to give the user time to change the switches.
So we're trying, how we can use switches, or we're trying to program assembly.
Well, just like in some of the software assignments, you were reading data from switches, right? You were reading data from the 11 and all zeros. Well, you would still have that, but you would also need to include some sort of delay so that after one set of data is inputted, there would be enough time for you to change the switches. And remember, one of the examples we did in class, it was one of the examples when we were talking about loops. I did an example that showed how you could get like a ½ second delay. All right, now, you know, the program that I did, you know, after I had everything working, right? I used I can't remember if it was an assignment or if it was one that I did on the board, but there was one software program where based on a number, based on whether a number was above or a certain, or above or below a certain other number, I think it was like 32,000 something. It would either multiply the switch data by 2 or divide the switch data by 4, something like that, right? See, that was the one that, you know, wasn't working, even though my Otter was good and, you know, everything. And you know, I built in a 10-second delay. So I put in the first data and it multiplied by 2 like it should. But when it was having the problem, it would never come back. Like I'd reset the switches to another input, but it would never take that second input. It would just stay at the first one. It was almost like an infinite loop or something. But like I said, it was just that I guess the program had to be restarted, you know, because then it started working. So anyway, you know, if you're dealing with switches or if you're dealing with your outputting to the same device periodically, you're going to have to put in like a delay. But everything else, if your program was working in RARs, you know, without that delay, I mean, that should all be working still. And provided you do the delay correctly, it should all stay working. But again, you can test it in RARs.
Is there a way to interface RARs?
Oh, right, yeah. How do we do that? The mem file. Okay. Yeah, because that was one of the first assignments. Remember, you made a mem file and then you put it on Vivado and you made sure it was running through it. Yeah. So, right. Yeah. So whatever program you decide to use for this, yeah, you would make a mem file and then you put the mem file in Vivado, and your Otter should run that. And that's what this all test is too. It's a mem file that, you know, either Dr. Hummel or one of the other doctors came up with. Yeah. Now another thing is, and this should make you happy, is the sim file for hardware 6 and also the sim file for the final project is super simple. You know, you'll still have to, you know, generate a clock, but it's just, you want reset not to be activated. Like you would just reset to 0. And that's it, because the mem files are essentially your test cases, right? The 6 instruction program for hardware 6, that's essentially your test case. Right? And then, when you're testing it out, the all test mem file, that's your test case. And then here, whatever program you decide to do, that's going to be your test case, the mem file. And so the sim file for hardware 6 and the final project, super simple. Probably you'll never have another simpler sim file. Now, as I have mentioned before, for the final project, okay, not hardware 6. Hardware 6 is still the same groups as previous hardware assignments, so it's still a 2-person group. But for the final project, you can have groups up to 4 people. So, whether that's two-person groups combining, or whether that's, 4 totally different people from different groups combining, it doesn't matter to me. You just need to tell me before Monday, March 6th. Okay. So there can be 2-person groups, there can be 3-person groups, there could be 4-person groups, no 5 people or more. Okay, 4 is the maximum. If somebody wants to do it by themselves, they can. I mean, I wouldn't recommend it because it is a lot of work. I mean, the reason I'm allowing groups up to 4 is because it is a lot of work. All right, there's no way around it. Also, you're evaluated on the troubleshooting. So you're expected to find the problem. Now, I can give you guidance. I can tell you, hey, did you check this? Did you look at this? I can make sure that you're doing the process correctly, but I'm not going to sit down and look at your code and tell you where the problem is. You have to find it. Okay, you're graded on that. That's a part of the evaluation. Okay, also, like I mentioned at the beginning of the quarter, the first 75 to 80% or so of the class is in person. The rest of it is online. Now, what I mean by online is not that there's going to be online lectures or, anything like that. It's just that I'm going to be available on Zoom during the last 2 weeks while you work on the project. So there's no new material. It's just the last 2 weeks are dedicated for you to work on the final project. Now, remember, there's a final project hardware and there's also a final project software. We've got one more in-person class next week. Tuesday of next week, I'm going to talk about what the stack is and also how to do subroutines in assembly. And at the end of that class, I'll tell you more about the final project software. Okay, so the final project software, that's going to be due March 10th. Okay, the Friday before the last Friday. And then, like I said, this final project hardware is due the last class day, which is the 17th. Okay. Let's see, anything. Oh, and the grading criteria for the final project is different than what it was for the hardware assignments. And I have what the grading criteria is on Canvas. Okay, I didn't, I'll probably talk more about that on Tuesday, because that's when I'll talk about the grading criteria for the software final project too. But if you can't wait till then, you can look now and see what it is. Okay, last thing is that handout that's on each table. Like I said, that's optional, although I strongly recommend that you look through it. And you can see that I have the numbers up here. There's 14 questions. So during today's class, anyone can come up to the whiteboard and write what their answer is for any of those questions. And if it's correct, I'll put a check mark next to it. If it's not correct, I'll put some comments. Okay, hopefully by the end of the class, it's all filled out. But again, what's on that handout are examples of looking for patterns, which can help you make your code more efficient. Okay, so do you have any questions about anything I went over today? Is it clear what the distinction between hardware 6 is and hardware 7? Yeah, that was one of my main purposes of doing this, because I don't want you to get mixed up. I don't want you to be doing more than what you have to do for this, because this is due in a little over a week. And I want to make sure you do what you're supposed to do here and not leave something out, right? Because this is important, because it's the final project. I think it's worth like 12%, something like that, if I remember right in the syllabus. Okay, well, if there's no questions, you have the rest of the time today to work on what you need to work on.
Oh, yeah.